where we were able to talk about organic, we were able to talk about inorganic, okay? And in today's lesson, we are going to talk about physical chemistry. Yeah, like how we discussed in our previous lesson is, remember when we were introducing all those branches, when we introduced physical, inorganic and organic, we discussed, we agreed, I like using that word because we have to agree. It's not that we have to agree, it's not that whatever I tell you is an absolute truth, okay? The teacher must convince you, and if you fail to agree with the teacher, then the teacher should try to do, to bring this, bring that, bring this, until when you agree, the two of you agree. And that's what we call learning. So usually that's why I usually say we agreed. So we agreed that chemistry is divided into 3 branches, whereby we have organic, and this one deals with compounds of carbon, okay, apart from oxides of carbon, that is carbon monoxide and carbon dioxide, okay, apart from hydrogen carbonates and the carbonates. Now this is organic chemistry. Then with physical chemistry, we talked about inorganic chemistry. Now this one deals with all other compounds apart from the organic compounds. All other compounds, okay? Apart from the organic compounds. And so that's where we shall talk about these ones, these exceptions. We shall talk about them in organic chemistry together with other inorganic compounds. Then we have physical, okay? Physical chemistry as another branch, okay? As we are going to introduce it today, as we are going to talk about it today. And this one, it deals with the behavior of these chemical compounds in different conditions, okay? And those are the topics we shall have, okay? Whereby we shall have topics like, we shall talk about the pressure, the laws, the pressure laws, that is the Boyle's law, Charles's law, Gay's law, and then we get that Moore gas equation, the overall equation, and we use that equation to do different calculations. Then we shall find topics like correlative properties and stuff like that based on the course outline, which is just on our next slide. So with physical chemistry, the first topic is we shall talk about matter, okay, and talk about the particle nature of matter and the different states of matter and how particles behave in those different states of matter. And here it will just be like a reminder of our senior one work. Then when we finish the particle nature of matter, we shall talk about the atomic structure. Yes, we talked about the atomic structure in inorganic, where we wrote the electron configurations and stuff like that. Here we shall go deep, okay, as far as an atom is concerned. Then we talk about correlative properties. We talk about correlative properties and how they do affect, okay, or how these correlative properties are affected or can be determined based on the different solutions, and okay, and we do those calculations. Then we talk about bonding and structure. Yes, in inorganic we talked about bonding, where we introduced the types of bonds that do exist. Now here we shall talk about more of structures. Okay? Then away from that, we talk about phase. Talk about now here the phase equilibria. We studied the different phases that can exist. Okay? That a compound can exist into, whereby a compound can exist as a solid, or as a liquid, or as a gas. And we see how this equilibrium can be varied, how pressure and temperature change can affect the equilibrium of different compounds in given phases. Then we talk about thermochemistry. So here we shall deal with the heat changes. You know that for a chemical reaction to occur, then heat is either absorbed or heat is given out. So basing on these changes, then we can determine how speed a chemical reaction is going to occur, how a chemical reaction is going to occur, whether a chemical reaction is going to be feasible or not feasible, and we shall see all this in thermochemistry. Then we talk about physical equilibria, and then chemical kinetics, the speed at which the chemical reactions occur, and how you can increase the rate of attaining different products. And this one is important as far as industrial chemistry is concerned. We shall talk about it. Then we talk about chemical equilibria, the Kas, Kbk, stuffs like that. And then ionic equilibria, and finally electrochemistry and electrochemical cells. So if we cover all this, then you guys will be good to do your name. So I've given you the course outline. Now at campus, when you are given the course outline, then the lecturer is said to have taught. So likewise, I have taught. Even if I close the laptop and go, I have taught. So you have the course outline, you have the notes in the classroom, you have I posted for you some books, the Campbell and some other Cambridge book. You can sit down and read. You can decide to read ahead of us. And maybe we finish particle nature for you, talk about corrugative properties, atomic structure, and then you come back for some little explanation so that during lesson time for you work hour. Okay? But it's all the issue is studying, and yeah, you get the content. Yeah, so basically this is the course outline. And as always, we shall start with our first topic, which is matter, the particle nature of matter. Okay? And this is, we shall just cruise here. Because matter, right from senior 1, you've been studying matter. Okay? You know what matter is.
I'm fine, sir.
Anything concerning, you know what matter is. So we shall just cruise. So particulate comes from particle and particle nature. Now from senior 1, we were taught that anything that can occupy space and anything that has weight is matter. And we shall not deviate from that. Anything that has weight and anything that can occupy space is matter. In other words, anything around you, you can have a look. You rotate your eyes around you. Anything, both what you can see and what you cannot see, it's all matter. Okay? And so now, Therefore, matter can exist in two solids, gases, and liquids. So you know that's simple chemistry. That's in your own chemistry. Now, if you are to study deep, if you are to go deep, you find that matter is composed of particles. Okay? Matter is composed of tiny particles that you cannot see with your eyes. You can't see the particles with your eyes. Okay? And those particles, they are called atoms. Okay? And so these atoms are arranged differently in the three states of matter: in solids, in gases, and in liquids. And so they do exist in three forms. We have solids, we have gases, and liquids. So we shall do some marathon here because things are a bit cool. And all matter is made up of particles. But the way these particles are arranged in solids, liquids, and gases, they are arranged differently. Okay? Yes. So that is the particle nature of matter. But these particles are not assumed to be stationary. Okay? These particles, you may feel that here, since they are particles, so the particles are just there within their main positions. No. These particles do possess energy, and so they move, they randomly move, okay, in any order, in any zigzag manner, from one position to another position to another position. However, the rate at which these particles move within a solid, within a liquid, and within a gas increases with increase in temperature. That when you decrease the temperature up to negative 273, okay, degrees Celsius, that is up to the absolute temperature, which is 0 Kelvin. This is the absolute temperature. Then at this temperature, it is assumed that these particles are stationary. They possess no energy, so they remain within their main position. But any temperature above this absolute temperature, then the particles will move. Okay? They will keep moving. But the rate at which these particles move is different from how they move in solids, different from how they move in gases, and different from how they move in liquids. A moment, guys. Yeah, it's okay, guys. So the kinetic theory assumes that these particles do possess energy, okay, and they are in random motion. They move in a random zigzag manner at any temperature above the absolute temperature, okay. And by the way, the also movement increases with temperature. So increase in temperature increases the kinetic energy, and so when you increase the kinetic energy, then the rate at which these particles are going to move is going to increase. So behavior of particles in solids, this is still senior one work. However, there is nothing obvious. When you are teaching, you don't take things to be obvious. So particles in solids are closely packed, like how you can see. Okay? You can touch any solid around you. You can try to box any solid around you. So because particles are closely packed, then solids have that definite shape that they have. Solids are solids. Okay? So the particles are closely packed in solids, and they are within the fixed positions. Why? Because they are closely packed with strong forces of attraction within these particles. Then they just oscillate, they just vibrate within their mean positions, okay? But they are unable to move, okay, from one region to another region, okay? And so when you increase temperature, obviously they do absorb the energy and they vibrate, they do oscillate within the positions that they do have, okay? Now those are the solids for you. That if temperature is increased beyond a certain degree, okay, then these vibrations, these mean vibrations within their own positions, within the positions of particles, do increase, that the intermolecular forces of attraction holding these particles close together, you can have a look. The forces of attraction holding these particles close together, they end up breaking down. And so when they break down, now the particles become free to move, okay, within the overall structure of a solid. And so if the particles become now free to move, then that's when your solid is going to melt, okay, and turns from a solid to a liquid. For instance, you can have your ice, okay? Your ice, it's a solid block, okay? And so when you heat the ice, the particles within the ice, they're going to absorb heat, they're going to absorb heat energy, and if they do absorb the heat energy, then these the particles, they will start to vibrate, they will start to oscillate within their main position. And so the hydrogen bonds that hold the solid particles close together, they get broken or they get weakened, and so the solid particles will be able to extend, to move, okay? And so that's when you see the solid melting. And therefore this explanation can help you explain the variation in melting and boiling point. We are going to see what boiling is among different compounds, okay, among different compounds. So after knowing this, then you should not fail such a question. Why certain compounds have high melting points than the other? Why covalent compounds have weak, have low boiling points than ionic compounds? Why ethane has a high boiling point than
Good morning, Hannah.
ethane? So based on those differences, you should be able to explain any concept. Okay? That's brilliant. So you can have a look at how particles are arranged in solids. Okay? And let's have a look at how particles are arranged in lipids. So you can have a look. So particles in lipids are far apart from each other with weak intermolecular forces of attraction holding these particles together. And so because of that, then these particles are free to move, okay, within the liquid. That's why when you pour a liquid on the floor, then the liquid will be able to flow, okay? The liquid will be able to flow. Because these particles, they are able to move, okay, within the liquid structure. But for solids, if you pour a solid down, will it easily flow?
Hello?
Obviously it cannot. Why?
Yeah, let me lead.
Because solids are strongly, they have strong forces of attraction, and the forces of attraction, they hold these solid molecules close together that particles cannot easily flow. Not so? Yes. Now when you increase temperature, obviously these particles, they are going to absorb the heat energy, and when they absorb the heat energy, then their kinetic energies, the kinetic energy
Okay,
is
Hannah,
going to
we are two
increase.
in a house.
Yeah, it's okay, guys. It's okay now. Everything is okay. Now, so we saw in liquids that the particles are far apart from each other, and so they can easily move past each other. And we saw that when temperature increases, then the kinetic energy of these particles is going to increase, and so the speed at which these particles will move is also going to increase. That if energy is increased further up to a given point, then the particles will move further away from each other. And that's when you see these solid particles turning into a gas. Because particles will keep the intermolecular forces of attraction holding these particles close together. They'll get broken. Okay? They'll get broken. And so the liquid particles, they'll move further away from each other. And so they turn into a gas. So that's when you see that the liquid has boiled, or the liquid is evaporating. Okay? Evaporating. But also when, after you have boiled your liquid and you lower the temperature again, you cool the temperature again, okay? Then the other heat that was gained by these particles is going to be lost, and the liquid condenses again, turns into, sorry, the gas condenses again and turns into a liquid. Okay? And you lose the other energy. Then particles in gases, they are now, for them, they are very far apart from each other. You can have a look at this. So this is our vessel containing a given gas. Okay? And so these are the gas particles. You can have a look further away from each other. And so because of this, the intermolecular forces of attraction holding these particles are so weak, so weak, that they are even overcome at very low temperatures. Okay? They are overcome at very low temperatures. And so the speed at which these particles move past each other is so high compared to how liquid particles move, compared to how solid particles move past each other. And so what does that imply? The gases can easily, they don't have a shape, they occupy, they can easily, so gases, they are gases. I don't know how to phrase it, but a gas, it's a gas, and a liquid is a liquid, and a solid, it's a solid. Why? Because of the behavior of the particles within these gases, solids, and liquids, and the forces that keep the particles close together within gases, solids, and liquids. So when the temperature of a gas is increased, the particles move further but tend to collide with one another. And so based on those collisions, then you can determine a chemical reaction can occur. We shall study chemical kinetics, okay? And see how temperature increases the rate of reaction. We shall see all this, okay? So evidences to show the existence of particles in matter, it is deduced from the experiments such as the Brownian motion and diffusion and if you consider Brownian motion, here you try to observe the dust. There's some good example I usually use. If you are in a room and the room has no ceiling, okay, and maybe in the iron sheet there is some hole, in the iron sheet, and then it's on a bright sunny day. You try to observe through that light, that ray of light that is penetrating through that tiny hole. You observe dust particles in a random zigzag manner. This small particles in a random zigzag manner. So also this guy Brown, he observed smoke particles under a microscope. Okay? And so when he observed smoke particles under a microscope, this guy was able to see the behavior of, he saw some tiny particles, okay, that were behaving in such a manner, in such a random zigzag manner. And the speed was so high in gases than in other substances. And so because of this, he was able to deduce that probably these particles, before that, he was able to deduce that probably matter is made up of tiny particles. That in a gas, those tiny particles are in a random zigzag manner. And also the same thing, the existence of particles in matter, it can also be illustrated using diffusion in liquids, whereby I think you perform this. If you get your beaker, I hope that's a beaker, and you fill it with water, okay, and then you add there, you get, maybe you can use copper to sulfate, it will give you the same thing, or you can use potassium permanganate solution, okay. So you get crystals of copper to sulfate and crystals of potassium permanganate, and you dissolve them, okay. You just get the crystals and you throw them. Now the crystals will sink at the bottom. Why? Because the crystals are more dense than the water. And after sinking at the bottom, then the blue color for the case of copper to sulfate and the purple color for the case of potassium permanganate, depending on what you've used, it is now going to gradually spread on its own throughout the entire solution. Okay? It is going to gradually spread throughout the entire solution. Now, the spreading indicates that diffusion occurs in liquids. You can have a look. So if this is your water, okay, and you add there the crystals of maybe copper to sulfate, the copper, it will settle at the bottom, okay, and then after, the particles will spread gradually throughout the entire solution. That at the end, okay, if you give it some time, this solution will end up becoming, the entire solution will end up becoming blue, or the entire solution will end up becoming purple, depending on what you've used, okay, which tries to explain the existence of particles, okay. And so how do these particles move? By diffusion, where it is the movement of particles from where they are more concentrated to where they are less concentrated across or along the concentration gradient. Good, it is not defined as movement of particles from the region of high concentration, the region of low concentration. For the people I've taught, you know why I don't like such a definition. Because when just say region of high concentration, I'll say high concentration of what? Because concentration means part of something over a whole. So if you just say high concentration, the region of low concentration of what? It won't make sense. So diffusion, particles move from where they are more concentrated to where they are less concentrated. So similarly, when you put your copper 2 sulfate, okay, in a beaker containing water, the copper 2 sulfate is going to first settle at the bottom, and then after settling at the bottom, then gradually the color of the solution, the blue color, is going to gradually spread, okay, throughout the entire solution by diffusion. Okay, you can have a look. It is going to gradually spread, okay, throughout the entire solution by diffusion. Similarly, when you use potassium permanganate, it's a purple solution, and you dissolve it. You just fill the beaker with water, and then you get crystals of potassium permanganate, and you put them in that water. The crystals will first settle at the bottom, and then after settling at the bottom, then the color, the purple color, is going to gradually spread the entire solution. That in the end, the entire solution is going to end up becoming purple, or this entire solution is going to end up becoming blue. So that one illustrates why aren't they? Why? Think about this. Why isn't the color spreading from maybe the color? Maybe let me try to illustrate. Let me try to illustrate this, and I do this. So you get your crystal of potassium permanganate, and you dissolve it, and it settles, and then gradually the blue color, where this one is more intense blue, this one is kinda colorless. So why isn't the color spreading from colorless? I don't even know how. Okay, so this one illustrates that particles move from the region where they are high to the region where they are low along the concentration gradient. In gases, it's the same concept, okay? And here we can use iodine, okay? Whereby you heat your iodine vapor, okay, in a beaker, and then after heating the iodine vapor in a beaker, then you get another clean beaker, okay? And you cover it here. The beaker is completely white. There is nothing, and you cover it here. So you can see some vapor that is coming out. So you put iodine at the bottom, and then you heat, okay, and then after heating, then you get the clean beaker, dry beaker, and then you cover it here. So what is going to be observed? Simply, this clean beaker, which is completely white, it is going to gradually turn to reddish brown. It is going to absorb the color of iodine. Why? Because the iodine being concentrated in this beaker, it is going to gradually diffuse through air until when it fills, that in the end of the experiment, all these two beakers, they will all have the same color. They will all have the same color. And so what does that mean? Diffusion has occurred. But when you remove this beaker again, then the iodine, if it was dry, then the iodine will diffuse out of this beaker, and the beaker will become white again. You put it back, the same thing. So these two experiments try to illustrate diffusion in liquids and diffusion in gases. But diffusion cannot occur in solids. Why? Because particles are close together, so they cannot move. Okay? So even if you get copper 2 sulfate, okay, and you put it maybe solid. Let's say you condense this water. This is ice. You condense this water into ice. This is ice. Okay, and then you put a crystal of copper sulfate here. You can't convince me that the crystal of copper sulfate, it will spread throughout the entire solid. You can try it at home. Yes, it might dissolve because this is ice water, this is water. But it will dissolve and stay here, just here. It won't be able to diffuse throughout. Why? Because the particles are stationary. The particles are not in motion. Okay? Yes. So let's talk about the gas laws. And from kinetic theory of gases is the theory that it is put forward to explain the behavior of molecules in gases. And before you explain the behavior, you need to know the properties. That gases are compressible. Yes, you can squeeze a gas and turns into a liquid. That is liquefaction. You can also squeeze a gas that is a liquid into a solid by lowering temperature and increasing pressure. You squeeze, you compress that gas until when it turns into a liquid. But for solids, no, they cannot. Low density, yes. The mass that can occupy a unit volume is very low. The mass of a gas which can occupy a unit volume is very low. So these gases have a low density. Gases can diffuse rapidly, well, yes, because particles move. The particles are free to move, and so because of that, then gases can easily diffuse. They expand when heated and contract on cooling. Most gases are colorless. Yes, most of them are colorless. And finally, they show that change in volume when pressure is changed. And so based on this, then we can come up to laws. And the first law is the Boyle's law. This was studied by Boyle, and he came up with a law that shows the relationship of pressure and volume. Now remember, for those who are studying gas exchange, you remember we are saying volume, pressure, volume. So this was studied by Boyle, and this guy came up with a law that says that at constant temperature, if you keep temperature constant, then pressure and volume, they are always inversely proportional to each other. Okay? Pressure and volume, they are always inversely proportional to each other. That is if you keep temperature constant. But now when you vary temperature, and maybe you keep one thing constant, maybe you keep pressure constant, then the volume, how the volume is going to vary, can be determined by the Charles's law now. Okay? So Boyle's law gives the relationship between pressure and volume. And this concept is so important as far as gas exchange in biology now is concerned. Because imagine, think about how you take in air. Okay? This is exchange, I'm writing example. Sorry, I said exchange and then I said for example. So, sorry for that. So think about how you take in air. Can you take a deep breath? So are you seeing how the rib cage is varying, is moving? Yes. So it is moving upwards and outwards when you are taking a deep breath. So this pressure volume concept is used so much in gas exchange, whereby the gases move from a high pressure to a low pressure. But we have seen that pressure and volume, they are inversely proportional to each other. So therefore, for you to decrease the volume in the chest cavity so that you take in gases, so for you to decrease the pressure in the chest cavity so that gases can diffuse inwards, then the volume of the chest cavity must increase. So that's why the rib cage moves outwards and upwards. Okay? And then the diaphragm contracts. Then for you to push out the gases, the pressure inside must be high than the pressure outside. Okay? So that's when the chest, okay, is going to, the rib cage is going to move inwards and downwards. And then the diaphragm muscles relax so that volume inside reduces and pressure inside increases past the atmospheric pressure. And then the gases are expelled out. So this is horizontal integration of knowledge. We are using a chemistry concept to explain a biology concept. Okay? So if you can integrate these concepts together, then you are good. Then you know what science is. Okay? Yes. So I hope you remember you studied gas exchange in ODEV. So you can use that. You can try to recall that. So this law, it's not just a mere law, but it is important as far as nature is concerned. So volume, pressure and volume, they are inversely proportional to each other. Okay? So when I remove the proportionality sign, okay, then I will introduce the proportionality constant, okay, and so it will end up being pressure is inversely proportional to V. So pressure is equal to kV. So if I bring this V, then PV is going to be equal to a given constant. So this is the Boyle's law. This is the Boyle's equation. Mathematically, how it can be represented. Okay? Yes. So Boyle's law can be volume is proportion or is inversely proportion to P, and if we introduce the proportionality constant, then PV is going to end up equaling to K. Now assuming you have the volume of a gas, assuming that you have volume V1 of a gas and pressure P1 of that gas, the volume, it is in a closed vessel, okay, you have volume V1 and the pressure is P1 and the temperature is constant. Now when you vary the pressure, okay, of this system, can you determine, and you keep temperature constant, can you determine how the volume of this gas is going to be? Remember, if you want to compress the gas, you increase pressure and you decrease temperature. But here we are keeping temperature constant and we are increasing pressure on this gas. Is the volume going to increase or the volume is going to decrease? They are inversely proportional. So if you increase pressure, then the gas becomes squeezed up and so the volume decreases. And so how do you get the volume to? So from P1, okay, from P1, V1, which is equal to a constant, therefore P2, okay, V2, it is also equaling to the same constant. The constant is the same, okay, the constant is the same. So whether you vary, the constant will always be the same. So I'm not wrong to equate, since the constant is the same. I'm not wrong to say that P1 V1 is equal to P2 V2. So from this expression, therefore, I can determine how the volume is going to vary when pressure is increased from P1 to P2, or when pressure is decreased from P1 to P2. Not so. So this is the Boyle's law. This equation is important as far as pressure volume changes is concerned. Not so? Yes, that's brilliant. That's brilliant work. So V1 P1 is going to be equal to P2 V2. For example, let's do some quick math. Some quick math. So you have the volume of a fixed mass of a gas and pressure of 4 atmospheres. So you have pressure, which is 4 atmospheres. And you have, this is pressure 1, and you have volume 1, which is 200, okay, centimeters cubed. Now, they want you to calculate the volume when pressure, okay, at the pressure of 1.2 atmospheres. I think this was, sorry for this, the pressure was decreased from this to 1.2, 1.25 atmospheres. Sorry for this. So the pressure was decreased from 4 to 1.2 atmospheres. So we want volume 2, okay? We don't have this, but we have pressure P2, which is 1.2 atmospheres. So really, can't you do this? Can't you do this really? So from P1, V1 equaling to P2, V2, not so? So what is P1? It is 4 times V1, it is 200. It should give us V2, which we don't know, times the 1.25. So therefore our V2 is going to be 200, which is 800 times 4. Okay, let's say 200, and then out of 1.25. So people with a calc, can you do that for us? Maybe let me do times 100 here, and the same times 100 here. Since you don't have a calc, so this is going to be 125 by 25. Okay, by 5. 5, this is 2. This is 25 by 5. This is going to be 50. So somebody with a calc, you can help us. So this is 50 times 4 times 100. Somebody with a calc, then by 25. This is 1 by 25. This is 4. And then by 100, this is 1. By 100, this is 1. So the answer is going to be 50 times 4, and then times 4, which is 200 times 4, which is 800. So the answer is 800 centimeters cubed. So are you seeing that pressure and volume, they are inversely proportional to each other? When pressure is decreased from 4, okay, to 1.25, then the volume has increased from 200 to 800. So basically, that's how simple Boyle's law is. Not so? Yes. So if you have been confused with this, the way I've calculated this, don't mind. You'll be having a calculator. You just put this in a calc. 200 times 4 out of 1.5, you get the answer. But here, since I didn't have a calculator and people didn't come with a calculator, I think they were there, but I didn't give them time to. Then I had to do all this. I had to go through all this. And I won't discuss this is mad. I won't discuss this. That's mad. So basically, that's how simple it is. Not so? Yes. So that's boil 0. That's boil 0. Okay? So that's how simple the calculation is going to be. Now graphically we can represent boil 0. Okay? On a graph. Whereby if you plot a graph of pressure against volume. Okay? Where you put pressure on the x-axis and volume on the y-axis. Still, even if you put volume here and pressure here, you still get the same curve. Okay? Then we shall get such a curve. What does this curve show? That at low volume, in fact, it's volume which should be here. Okay? And then pressure should be here. Why? Because it's pressure which affects volume. But then if also volume increases pressure, so they also affect each. So at lower volume, for instance, let's have a look here. Okay, you see the pressure is going to be high at constant pressure. Then when you increase volume and pressure remains and temperature remains constant, then the pressure decreases. But now when we increase temperature from T1 to T2, then the variation also changes, but it still follows that same trend. Okay, whereby you can have a look at lower volume. Okay, the pressure is high. Okay, but when you increase volume from V1, maybe this was V1 and this is V2. Okay, then the pressure, you can see it is going to decrease. But the volume, at any volume, the pressure is always high for temperature T2, that is higher than temperature T3. And the same is valid if temperature is increased from temperature T2 to temperature T3. And so how do you get this curve? By plotting PV, which is equal to a constant. So you first find a constant, the proportionality constant, and then you vary volume, P1 V1, from this P1 V1 equals to P2 V2. So from this, you can get such a curve. Given any plot, if you have told you to plot anything, plot this out against this again, you can get it. Not so? Yes. Then let's have a look at this guy called Charles. Before Charles. Now if you plot pressure against 1 out of volume, now depending on which curve is given, and you plot pressure against 1 out of volume, then we shall get a straight line with a positive gradient, and the straight line passes through the origin. So depending on which graph is given. So also I can give you this graph and I say calculate the pressure, or calculate the volume when pressure is at maybe Y. Okay, so you come get this value and then you come and read this 1 over V. So remember, this will be 1 out of V, but for me I want volume, so the answer you get, you just take the reciprocal. Okay, and you get the answer. Or you can say calculate the pressure at 200 degrees at 200 centimeters cubed, and then I've given you a plot of 1 out of V, and you've plotted 1 out of V, and you've gotten a straight line. But for me, I want the pressure at this. So you convert this to 1 out of V, okay? And you get your 1 out of 200. And this is something like 0.005. Fine, you fact check this. And then you come at 0.005, okay? And you read this pressure here. But otherwise, if you are to look for 200, when me have given you this, then it will be just a tag of war. So basing on what is given, then you can determine the pressure or volume at any temperature. Then for Charles' law, like I told you earlier, Charles' law, we get the volume, okay, when temperature is increased and we keep pressure constant. From Boyle's law, you see the two, they are concurrent. The two laws are concurrent. Boyle's law shows the relationship between pressure and volume. Okay? But now, how about if we keep pressure constant? Now, for Charles' law, for Boyle's law, it occurs at constant pressure, constant temperature. But now, how about if we keep pressure constant and we vary temperature? What will be the volume that we shall get when temperature is varied and pressure is kept constant? It is given by the Charles law. Whereby now, the Charles law tells us that the volume of a fixed mass of a gas or a given mass, the mass is not changing within that reaction vessel. The volume is the same, okay? But you are varying temperature. So how is it going to change? I mean, you are not adding any gas within that closed system, within that system, but you are changing, you are varying the temperature, and you are keeping the pressure constant. Okay? Then the volume is going to be directly proportional, okay, to temperature. So if temperature increases, then the volume also does what? Does increase. If temperature decreases, then the volume does what? Decrease. So that's why when you want to compress a gas, then you vary temperature and volume, whereby you vary temperature and pressure, whereby you're going to increase the pressure and then you decrease the volume. Oh, you decrease the temperature. So therefore, we shall reach a level where we shall combine the two laws. Because now you want to compress a gas, or you want a given volume of a gas. How are you going to vary temperature and volume? Sorry, what's wrong? How are you going to vary temperature and pressure to get that given volume? That's all. You think about that. Think about it. Think about it. So therefore, if we make the constant, therefore V out of T, because we shall just divide by T here, divide by T here. Okay? Then we shall have V out of T to be equal to the constant. So therefore, if the temperature of a gas is increased from T1 to T2, the same. So if you have V1, okay, out of V1 out of T1 equaling to T to K, and then you also have V2, which is our new volume that we don't know, and T2. Remember, we increased temperature from T1 to T2. It should also be equal to that constant of proportionality. So it doesn't stop me from equating V1, okay, out of T1, okay, sorry for that. It doesn't stop me from equating V1 out of T1 to V2, okay, out of T2. So as simple as that. Okay? So this is the equation that we get from Charles' law. it is still, I hope it is still easy. Let's have a look. Do you have an example before that? Assuming you have maybe at constant pressure, okay, of maybe 1 atmosphere, 1 atm, the volume of a gas is maybe, let's say, 1 decimeter cubed, okay, cubed, and the temperature is 25, okay, centimeters cubed, okay. Yes. But if temperature is increased from 25 maybe to 100, okay, centimeters cubed, what will be the new volume of a gas in in decimeter cubed? So can you do that chap chap? And now to do this, you have to convert this temperature into the Kelvin scale. So where it will be 25. Anyway, even if we convert, we shall still get the same answer. But we first convert the temperature into the Kelvin scale, which is 275. Okay? And then this is 298. Okay? And then 100 plus 273. This is 273, not 5. We shall get 373. So from T1 V1, so from V1, which is 1, out of T1, which is 298, okay, it should give us V2, which we don't know, out of 393. So therefore our volume 2, is it going to increase? Yes, it is going to be 393 times 1 out of 298. So what's the answer here? This is 298. So the answer must be 1 point something. And so you can see decimeters cubed. So you can see that there is an increase in the volume. What's the answer?
It is 1.25.
So the answer is 1.25. So 25. So do you therefore notice, do you therefore see that there is an increase in volume? Yes. So this is Charles's law. Charles's law. So for Boyle's law, it gives the relationship, okay, of volume and pressure at constant temperature. But for Charles, it gives the relationship when pressure is kept constant, okay, this is inverse, when pressure is kept constant but varied the temperature. So if you understand, this is just a summary of the two laws. So graphically, we can represent Charles's law as this, whereby this is a plot of volume against temperature, okay, and we shall get a straight line that you extrapolate, if you extrapolate the straight line, okay, up to this absolute temperature, this is absolute 273, which is 0 Kelvin, this is negative 273 K, then you shall get the fixed volume of that gas. So the dotted line is the theoretical expression of Charles's law, since any temperature that is less than 0 causes the gas to undergo compression. And you have such an example. Actually, it's the one I've just given. So the volume of a fixed mass of a gas at 25 is this. So calculate the volume of a gas at 10. You can do that. You can do that. Just chop chop. So can you hurry up?